Good morning and welcome. We are Apex Tech. We are here to present today our design review for our higher power RF transistor test board. I'm Alex Huntington-Meath. I'm the leader of our group and I'm an electrical engineering student at NCA&T.
My name is Tariq El-Kibalon. I am a computer engineering major here in North Carolina A&T, and I am the team analyst.
I'm John Williams. I'm an electrical engineer here at A&T, and I'm the team spokesperson.
My name is Craig Satchel Jr. I am the optimist and pessimist of Apex Tech. I'm a computer engineering student here at North Carolina A&T State University.
And my name is Kadira Malvo. I am the recorder for Apex Tech, and I'm a computer engineering major here. And now on to the overview, our objective. Our objective is to assist Northrop Grumman by evaluating RF transistors, and this is to increase the body of knowledge on LD-MOS and gallium nitride, and we will do this by high power RF transistors through third party. Now a quick overview. Today we will be talking about our requirements, and then we will be showing you our design review, and then our tentative schedule for our project, the Gantt chart, and then our cost of summary, which is all of our products together.
Thank you, Kadir. As you can see right here, this is our requirements specifications table. At least half of it that we derive from our customer. As you can see here, these first two are mapped to the first marking requirement we got from our customer, was that the test bench should be able to verify power and transmission parameters. With that being said, we derive two engineering requirements that correlate to that. The first being that the test bench must be able to measure RF parameters such as output power, power density, gain, efficiency, and all these parameters must be able to measure them within the IFF band, L band, and S band. And then the other engineering requirement we derive from being able to verify power and transmission parameters is that the test bench must be able to record input to and input from connected transistors. Furthermore, concerning the other marking requirement derived from the customer, that technology utilized should be in compliance with government privacy policy. The two engineering requirements that we derived from that one was that the transistor manufacturers must have a sales office within the U.S. and that the transistor manufacturers are Department of Defense accredited suppliers. Moving on, the next engineering requirements that were derived from the marking requirement that the test bench should be able to test gallium nitride and LD-MOS transistors. The first engineering requirement is one that we modified since our previous project proposal in order to make it more in line with the marketing requirement number 3, and it's such that the output of the LD-MOS and gallium nitride transistors should have a max 10% tolerance range within the corresponding ADS simulations output. And then furthermore, in correlation with being able to test gallium nitride and LD-MOS transistors, the test bench must be able to prevent damage to the connected transistor from overheating. And then our last marking requirement was that the technologies utilized in our test bench must be readily available and compatible. In order to meet that marking requirement, we created the engineering requirements that the tested transistors must be commercial off-the-shelf products as defined by the Department of Defense. The tested transistors are currently being produced by manufacturers, and the tested transistors will still be in production within the next 2 years.
Thank you, Tari. Moving on, this is part of the beginning of our design review, the block diagrams. This is the level 0 block diagram. As you can see, there's going to be 3 inputs. That's the RF transistor itself, user frequency control, and 120 volt AC power, your standard wall power. And the only output is real-time electrical data that will be monitored by software on the other side. This is our level 1 block diagram, giving us some more detail. We've broken it into the components of the signal generator, which has inputs of signal generator DC voltage, your standard 120 volt AC power, and user frequency control. Its only output will be the RF generated signal that will go onto the matching system. The outputs for the matching system will be the attenuated input signal and an input signal that moves to the evaluation board. The evaluation board has the inputs of evaluation, DC voltage, the RF transistor, the input signal from the matching system, and its only output will be the attenuated output signal that goes to the output monitor. Output monitor's inputs will be that signal, the attenuated input signal from the matching system over the top there, and 120 volts AC power from your standard wall outlet as well. Power supply, which we had done in detail in our design documents, will have 120 volt AC power as its input, and outputs being the signal generator DC voltage and evaluation board's DC voltage. The only output on the output monitor will be the real-time electrical data mentioned in the prior block diagram.
Thank you, John. Part of one of the requirements of our presentation was to illustrate our project or our system using a UML diagram. Now, we decided to go through a few UML types of diagrams, including the physical diagram and also the activity diagram, but ultimately we decided on the use case diagram. Now, the use case diagram illustrates the system from the user's point of view. Now, what you will see here are a few stick figures, which stand for actors, which they basically interact with the system. The rectangle itself is the actual system, and inside this rectangle, you will see ovals, which represent the use cases. On the left side, those actors are actual human actors, and on the right side of the diagram, you will see software type of actors or systems that interact with the system. Now, these use cases, from the user's point of view, are monitor the S-band frequency, monitor the L-band frequency, also monitor the IFF band frequency, and validate transistor functionality. Now, we'll be using the LabVIEW software package to record the measurements from our system. Here you will see our Gantt chart, which is basically the bar graph representation of the timeline for our project. You can see here that we have 3 major phases: board design, which is going to be 48 days, construction 38 days, and testing, which is 21 days. Now, this timeline spans from the end of November to the mid-April. Pretty much all these activities are on the critical path, except for the transistor ordering and the software interface development. Other than that, all of these have time constraints and need to be done promptly on time. I'll now pass this off to my colleague Alex.
Thank you very much, Greg. The cost summary is simply the collected estimate of the parts that we will need to purchase in order to construct the test bench system. As you can see here, we need an RF switch, a device to route the high frequency signal through the transmission pathways mini circuits, a driver amplifier, a device that will basically increase the power of the signal, a preamp power supply, which again is used to boost the supply, the power supply to the main amp. A storage capacitor, which will be used to, will be powered up and will be used to supply power beyond what is used in the regular needs. The RF transistor evaluation board with spare transistors. This is sort of the heart of the system. It will be the test benches will be replaced as we put more boards on, or as we place more transistors on, and they will be within the 3 bands that we need: the IFF band, the L band, and the S band. A 50-volt power supply, which will be the main power supply for the system. An RF power divider, which a couple defined amounts of electromagnetic power to the transmission lines to port to enable the signal in the mini circuits. And then RF coaxial cables, which will basically tie the whole system together.
Do you have a total?
We did not subtotal that system. We'd be happy to do that though. We actually know that estimate isn't quite correct anymore, as we have some revised figures on several different things, but they were We do not have them at the time that we generated this table.
Thank you, Alex. Now for our conclusion. As you heard, we gave you the engineering requirements, which can be traced back to our marketing requirements. Then we reviewed our design through block diagrams and the use case UML diagram. Then we gave you our tentative schedule through the Gantt chart, and then we gave you our cost summary table, which listed all the parts that were needed for our project. Now I'll pass this off to Tariq for our demonstration.
Thank you, Kadir. So for our demonstration, we will be conducting a test as illustrated in our design documents within our test document. Our test document in particular only tests LDMOS, but for our demonstration, we will be testing LDMOS and gallium nitride transistors. As the process is the same, it's just that the parameters will vary by some volts. So with that being said, let me go ahead and open up the test document so we can get a chance to look at it. Alright, so in terms of the description of our test, we will be verifying that the level 1 block diagram, the evaluation board, can test LDMOS transistor technology via unit test. The way we're going to ensure this is that we're going to run a simulation on an ADS simulation for the LDMOS, and then compare the output of that particular LDMOS transistor against the real output of the transistor we'll be placing in our evaluation board in order to validate that the LDMOS transistor is actually functioning appropriately.
Thank you, Tariq. As you can see, the setup for this particular test is we're going to input an LDMOS RF transistor in the evaluation module. We are going to be looking at the voltage, the gate and drain nodes of the evaluation board. We will be sweeping the gate voltage from 0 to 10 volts in 1 volt increments, as well as the drain voltage from 0 to 50 volts in 1 volt increments. We're going to measure that drain current to the transistor's ADS simulation output and determine if the evaluation board is functioning correctly.
Now on to our steps. So for the first step, the action will be to build the ADS test model of the LDMOS RF transistor and recording to the manufacturer specifications. This is expected to have the result of the ADS module that should be able to simulate the LDMOS RF transistors functionality as prescribed by the manufacturer.
Secondly, we want to sweep and record the ADS test module of the LDMOS transistor, raise gate voltage from 0 volts to 10 volts, and the drain voltage from 0 volts to 50 volts. The expected result is that we should sweep the gate voltage, well, the gate and drain voltages, and store each combination and the resulting drain current. Now, as far as steps 3, 4, and 5, we are unable to demonstrate those at this time because we basically have not built our board yet at this stage in the process. But later on, we will be able to. Step 3 being place the LDMOS RF transistor into the evaluation board. Step 4 being sweep and record the gate voltage and drain voltage from the terminals of the evaluation board module at 1 volt intervals between 0 and 10 volts and 0 to 50 volts respectively. And lastly, comparing the drain currents of the ADS generated results and corresponding measured drain currents. Now I'd like you to focus your attention to our other monitors, which is going to show you the ADS software in action.
Again, thank you very much, Craig. This right here is the LDMOS example. As you can see, the LDMOS chip is right here, and it's just hooked up into a fairly straightforward set of parameters that will sweep the parameters as described from 0 to 50 and from 1 to 10, or from 0 to 10. You can see the results right over here. You can see that there's some compression across the top as it reaches the higher currents. However, this example is a decent example of what we should expect to see in terms of the LDMOS transistors. And if you'll step right over here with me, this is the GAN. Again, right here is the GAN transistor in basically the same setup with the altered parameters. As you can see, we're going from 0 to -2, and then we're taking that steps by 0.2, and then again, we're going from 0 to 50 in steps of 1. You can see the results right here. You can see that there's basically no compression across this, and we are reaching a considerably higher level of power across this system, which is what you would expect from a GAN transistor. Which I believe brings us to questions.
So we don't in the original we supposed to put some hardware. You say placed in the module. This contract place the transfer in the evaluation board. This means in the simulation or in the hardware.
It'll be in the hardware when we
So-
actually do the test.
Yeah. So this is the NA, right? We didn't do that yet.
No,
We haven't done that yet. Okay. So okay. So. Yeah. I think most part is okay. I like to see the whole list of the summary of the components and preview the update of the
cost
various-
For the costs.
the cost and the whole cost, and we see, and we probably need to involve some extra stuff to make sure we are okay for those things. And yeah, and then we can start the hardware test like in the beginning of the next.
Excellent.
Yeah. Okay. So yeah, it's fine.
Okay.
Thank
Thank you, sir.
Thank you for your time, and this concludes our presentation.
Okay. Thank you.